So we'll straight away move on to the crystal field theory of the coordination compounds. I will not be taking care of the valence bond theory as I mentioned at the beginning. So it would have been crystal field theory rather than the valence bond theory whenever we have mentioned. I mentioned about the valence bond theory, but not the valence bond theory. I was talking about the crystal field theory. So see, I will be speaking about the crystal field theory in details, and it is sufficient for the competitive examination. You can answer any questions from the coordination compounds. If you know the crystal field theory in detail, you don't have to have an idea regarding the valence bond theory. Much idea regarding the valence bond theory is not required, because mostly the questions will be coming from the application side. For example, magnetic property could be asked, color could be asked, stability could be asked, inner orbital, outer orbital complex may be asked, strength of the ligand may be asked, splitting pattern may be asked, electronic configuration could be asked. All these things can be answered by using crystal field theory only. So by using crystal field theory alone, you can answer all these things. So there is no necessity to study the valence bond theory in detail for the competitive point of view. For the board, it could be required, because they may be asking you to explain directly. They may be giving you the complex and explain the nature of the complex by using the valence bond theory. In that case, you need to detail the valence bond theory, but for us it is not required. We need only the crystal field theory idea for answering the questions from the competitive side. So we'll just go ahead, students, with the crystal field theory. Crystal field theory. Crystal field theory, we'll just go ahead. Right, in the crystal field theory, what will be done is, see, it is called as CFT, I'll write it again. This is called as CFT in short. Okay, so we will be going through the splitting of the d orbital in three different complexes, that is octahedral complex, tetrahedral complex and square planar complex. These three kinds of the complexes, how the splitting happens in the crystal field. Crystal field is basically, we are talking about the ligand field. Okay, what happens is, when the ligands approaches the central metal ion, d orbital will be splitted. For instance, for example, I'll take manganese, Mn+2, students. If you take Mn+2 ion as such, without having the ligand, so you have 5d orbital, right? It's a d5 configuration. Try to understand. Mn, manganese, atomic number of manganese 25. Atomic number of manganese is 25, that is 3d5 4s2, right? 2 electron, Mn+2 means it has lost 2 electrons, that means it has lost 2 s electrons. 2 s electrons has been lost, that means it is a 3d5 configuration. It's a 3d5 configuration. Mn+2, it is 3d5 configuration, correct? So what I mean to say is, I am trying to say, for example, if you take a complex of the manganese, I will take Mn water 6 times, Mn water 6 times 2 plus, or Mn water 6 times Cl2. Right, because it is 2 plus complex ion is. We are only interested in the complex ion. See, if the ligands aren't there, if the ligand field is not there, if the ligand is not surrounded, if the central metal ion is not surrounded by the ligand, then this d orbital will be degenerate. How many d orbitals will be having? D orbital, 5 d orbital will be there. That is dxy, dyz, dzx, dxy, x square minus y square and dz square. These many d orbital you are having. That is how many d orbitals you are having, students? You are having 5d orbital. 5d orbital, imagine there are no ligands, these 5d orbital will be degenerate. 3, 4, 5 will be degenerate. What is the word degenerate means? Degenerate means having same energy. This will be degenerate, that is having same energy. Having same energy. Having same energy. Right? Having same energy. This is degenerate having same energy. Now what happens is, students, if the ligand comes, what will happen? We have to understand. In the crystal field theory, what they had explained is how the splitting of the d orbital happens when the ligand field comes. See, I'll take two complexes for instance. This is the one complex. One another complex, for example, I'll take NiCl4, that is 2 minus, NiCl4 2 minus, or K2NiCl4, I'll take it. Okay, so how many ligands are there? You have 4 ligands are there. One more complex, let me take K2NiCN4 times, I will take it. This is the third complex, I will take it. Again, how many ligands are there? 4 ligands. How many ligands over here? 6 ligands. Let us make it clear. What is an octahedral complex? What is a tetrahedral complex? What is a square planar complex? All those things we will predict it. So before that, you try to understand, if there are 6 ligands are there, then it will be always a octahedral complex. No ambiguity in it. It is an octahedral complex. If there are 4 ligands, there are 2 chances will be there. Either it will be a square planar complex, or else it will be a tetrahedral complex. I will give you a shortcut, very important shortcut, to predict just directly. You can predict whether the given complex is a square planar or the octahedral if the 4 ligands are there. Those things we will take care. Time being, I will tell you, this is an octahedral complex, this is a tetrahedral complex, and this is a square planar complex. We can straight away tell by using the shortcut. Okay, by using a shortcut you can directly tell. That will take care afterwards. First try to understand how the splitting happens, students. Try understanding. This is an octahedral complex. That means you have an octahedron. You have an octahedron. We'll take one by one. That is, I'll go ahead with the octahedral complex, students. When the octahedral complex comes into the picture, octahedral complex is possible when there are 6 coordination bonds. 6 coordination bonds around the central metal ion, then it is an octahedral complex. Once we have done with the splitting, once you understand the splitting, all the properties can be predicted at once. It could be the geometry, it could be hybridization, it could be outer orbital, inner orbital complex, stability, everything will at once predict it. Okay, don't worry. So try to understand how the splitting happens. We have an octahedral complex which is a 6 coordinate bonds are there between the ligand and the central metal ion. How does it look like? The octahedron, you have a square, and above and below the square ligand will be present. 4 corners of the square you have a ligand, right? 4 corners of the square you have a ligand, and above and below the square you have ligands. Total you have 6 ligands will be there at the 4 corners of the square, and above and below the square you have 2 more ligands will be there. Clear? This I am talking about the ligand. This I am talking is about the central metal ion. About the central metal ion. Clear? Central metal ion. Right? So now, Mn, water 6 times Cl2 if I am taking. Manganese will be there at the center. You have 4 water molecules at the 4 corners of the square, and 2 more water molecules. One is above the square and below the square, right? So this is how the ligand will be positioned in the octahedral complex, right? Let us try to take a look about the d orbital of the central metal ion. D orbital of the central metal ion. See, what the crystal field theory or the CFT speaks is, CFT is all about the interaction between the d orbital and the electrons of the ligand. That's it. Electrons of the ligand. It is just the interaction between the d orbital and the electrons of the ligand. See, d orbital carries the electron. Ligand also carrying the electron, because ligand is a Lewis base, high electron dense species. When the ligand comes along with the electron, what it encounters is the d electron. Try understanding why it comes is because there is a central metal ion that is having a positively charged species is there, or the nucleus of the central metal ion will be attracting the electrons of the ligand. Ligand electron will be attracted by the nucleus of the central metal ion. But when the ligand approaches, what happens is, when the ligand comes closer to the central metal ion, that is towards this, by attraction between the ligand electron and the nucleus of the central metal ion happens, or the positively charged. But it will encounter the electrons of the central metal ion. So electrons present on the d orbital of the central metal ion will start having the repulsion. I mean, there is a repulsion between the d orbital and that of the ligand electron. So this is what spoken by the crystal field theory, and this is what is responsible for the splitting. Otherwise there would not have been any splitting expected. So what is happening is, d orbital of the central metal ion will have an interaction, or will have a repulsion happens between the d orbital of the central metal ion and the electrons carried by the ligand. So this interaction is responsible for the splitting of the d orbital in the different field.